Hello everybody, we have events, animation, I shouldn't call it really events and animation. We have event-driven behavior to talk about today. We have a little bit of radiosity to talk about, and a little bit on ray tracing left to talk about. I'm going to cover all this stuff today, so miscellaneous little topics, and kind of wrap up a few things with OpenGL as well. Remember that December 14th, which is coming up in about 2 weeks, all of your assignments are due. Cannot accept anything past the 14th. And it cannot accept work that's not submitted into the EMS as well. And remember that our final exam will run on 2 consecutive weeks. I'm going to offer it on the 12th, in which most of you will probably take it. But if you can't make it on the 12th, don't worry, you can take it on the 19th. I'm also going to be here on the 19th. Only offered for this course. We'll have those 2 weeks because some students have other exams going on. If you don't show up on the 12th, no problem. It won't count against your attendance. And if you show up on the 19th, that'll take you the 12th attendance. So you only get attendance for one of those 2 days, the 12th or the 19th. So it doesn't really matter. Hey, TA, can you tell them no basketball right now? Because it's kind of irritating. Okay, thank you. Ray tracing. Any questions before I get started, actually, and before the basketball ends, hopefully? That was a really bad idea to put a basketball court next to this classroom. So, anyway, in any case, if you don't have any questions, I'm going to continue forward with the concept of ray tracing, which we talked about last time. But I gave you some examples of it. I wanted to mention a few more things about it. This is lecture number 40 or something of that nature. Actually, let me tell you exactly which one it is. It is 40. Ray tracing is lecture 40. And I wanted to basically look at it in terms of the concept of radiosity as well. So this lecture is not an overlap. It's a slight overlap in terms of the definition, but it's not a repeat of the ray tracing information that I gave you last time, which is what we covered last week. So OpenGL is based on the pipeline model, as we know, with each primitives that are rendered one at a time. So we don't have any shadows except for tricks or multiple rendering or things. And there's no multiple reflections either, as a kind of a general concept. So if we want to, we can create those things, shadows, and in terms of the rendering. But we can also take different approaches to it in terms of the pipeline design. We can redefine the pipeline as well. Or we can also look at the rendering equation, ray tracing, and radiosity as 3 concepts that we can customize actually in terms of the rendering process to optimize the output that we're getting. So ray tracing is what we looked at last time, and it was only really the first part of this kind of concept that I'm getting into. So by definition, just refresh your memory, you follow the rays of light from the point source into the destination source and can account for reflection and transmission. So what we're looking at now is light intensity, and now we're looking at light directional flow. What is the light actually hitting in concept? And in this little picture here, we can kind of sort of see that, this is the source and it's coming out this way. Or is it really the source? It is the source. This is the camera view angle. This is the source, and we can kind of see how we can cast some shadows, shadow casting. And this is all part of the rendering process, by the way. Once we get our scene graph and we get our information in our hierarchy of elements, we apply algorithms to those elements to produce ray tracing, which is going to give us our natural lighting, visual effects, shading, shadows, anything that we want to create on top of the basic scene graphic. It is computationally expensive, as I mentioned last time, and we haven't quite solved this problem yet to make it worthwhile. And we don't have any default ray tracers. Actually, in most programs, we have to manually do things because it is very labor intensive, computational wise, especially for considering everything that has to go through the graphic pipeline. And you should be familiar with that structure, hopefully. It will definitely slow down the rendering process. So you should be able to handle all of the physical interactions in terms of computations. Ray tracing is not computational, it's theory in terms of the practice and what we're trying to achieve. Most rays do not affect what we see, and scattering produces many infinite additional rays that might actually occur from this. An alternative is ray casting, as I mentioned, but didn't really get into ray casting as a concept. So what is ray casting? Only rays that reach the eye matter. We don't worry about things we can't see. And then we reverse direction and the cast rays. And you need at least one ray per pixel in order to have something to calculate. So it's sort of like ray tracing, but we're not tracing and we're not following everything in the scene. It's just going to be casting light on objects, and so we can do a backward tracing kind of approach to it. Take the object and trace it back to the light source, and we say, is it going to be visible? Yeah, okay, then we'll just cast a ray on it and we'll see what the effect's going to be. So in the ray casting quadrics, we have becomes standard way. So ray casting is done. It becomes a standard way to visualize the quadrics, which are going to be implicit surfaces in the computer scene graph systems. So construction of the solid geometry system, and solid geometries look at the primitives that are solids. You build the objects with a set of operations, the union, intercept, the differences. This is all done for you automatically in VRML, and it's actually semi-automatic in OpenGL, but you can still, overlay things and then have, hidden surface removal and other algorithms applied to it to get rid of those pieces. So the ray casting in a sphere, in this particular case here, so the ray is parametric and the sphere is quadratic, so resulting in an equation for a scalar quadratic. If you can actually calculate this out, which we're not going to do, but if you could probably calculate out the entry and exit points of the ray, and no solution if the ray misses the object, obviously, but you can hit an equation that gives you the entry and the exit points of the ray through the object. This would matter if the object was translucent, and we'd actually see through it. It also matters if we're going to have some sort of property to the object that's going to further cast rays. So shadow rays. So even if a point is visible, it will not be lit unless we can see the light source from that point. So we can cast shadows or feeler rays to see if we're going to actually have anything to illuminate in that particular direction. We also have reflection as a concept, and this is just basically the concepts that are associated with it. We're not going to go through the implementation details because you're not going to do it unless you're going to do it, well, you're not going to do it in OpenGL either, really. It's just conceptual at that point as well. So, and you're certainly not going to do it in VRML. But in terms of reflection, so you must follow the shadow rays off of reflecting or transmitting surfaces. So the rays itself creates more rays, in essence, in terms of reflection. And the process is recursive, obviously, because we have to go recursively through all of the different object surfaces and cast the same technique over again that's going to be cast from the original surface. And then the reflection and the transmission, we can actually also include retransmission in this as well as a concept. But we have the ray source that if we do ray casting, we're going to recast out this way, and we're going to recast out this way into the light source direction, calculate what the distance might be, figure out the intensity. We'll get into the terms of radiosity in a few minutes that kind of correlate with that. We can come up with ray trees. So in trying to solve the problem of how are we going to do the ray tracing, how are we going to make this problem of the search space being so big, narrow it down into something more manageable, we can put it into a tree data structure essentially and create a graph or a scene or metrics or even a tree structure that kind of looks at all the items and figures out, well, how are we going to, from the visual eye in this particular case, how are we going to notice or examine the effects of the light on all of these objects that are in here. So we can have multiple different perspectives, and we can take this scene, put it out into a data structure as a tree structure, traverse the tree, then we know where the light that's actually being traced from. Gives us a better structure to work with from a computer science perspective. This, in terms of the concept from a graphical perspective, looks good and understandable, but how you're going to put that into ones and zeros to sort of do calculations on it, which is where the data structures and the tree actually comes into good use for that. So we have the different surfaces to account for, the diffuse surfaces. So theoretically, the scattering at each point intersection generates an infinite number of new rays that can be traced. So in practice, we're only going to trace the transmitted and reflected rays, but use a prong model, and we're familiar with prong from previous lectures, to compute the shade at the point of the intersection. So then we have radiosity. So radiosity works best for perfectly diffused surfaces. And I'm going to talk about radiosity next, but it works good for diffused surfaces, which are not going to cast. Instead, they're going to, we're really worried about the intensity of the light and what level of illumination are we trying to expect out of the object. So building a ray tracer, how are you going to do that? Well, it's best expressed recursively. You can move into recursion later. You can remove the recursion later, but the image-based approach for each one of the rays, you send it to a function, and then you send that a reflective model to another function, basically recursively finding a solution for where the light's going to be casted. So you find the intersection of the closest surface, perhaps, and you need the whole object database available. So complex calculations, limit the object types. So computing the light at the surface and then tracing reflected and transmitted rays from the surface to new surfaces. That's another approach. When to stop? Well, that's a good question. Some light will be absorbed at some point, or maybe even at the intersections. So you can track the amount left and figure at one point you're probably going to end up stopping when there's no light left to cast. Ignore rays that go off into infinity, obviously, and put large spheres around them. And then count the steps and figure out how many depth you really want to take it to in terms of your algorithm. So if you were implementing a recursive ray tracer, here we have a kind of a functionality put together. So for color C that equals this, we're going to basically look at return the background color of something, because the background color is what's being changed. The background color is going to be lighter or darker, depending upon how much light's being casted on it. In terms of what's going on, if we're going to create some shadows, we're going to create some effects, illumination effects with color. I'm not going to go through the C code for this actually, but this is Objective-C, using an Objective-C API with C programming language. So, but what we're looking at is basically just the concept of ray tracers, what goes into it in terms of its implementation. So for computing the intersections, we need to find the intersections, because then we can basically use those as the points of illumination and then kind of use that as the new light source that's going to be projected. So implicit objects, quadratics, planes, polyhedras, parametric surfaces, all sorts of different intersections might exist. And so we can basically define those in terms of their separate qualities, and then kind of work forward in terms of the ray concept. So I'm not going to actually get into a lot of the calculations. I'm going to basically just wanted to show you the differences between ray tracing versus ray casting, and some of the things that go into the implementation of it. But we really covered ray tracing last time in terms of the definition. So you're not responsible for any of the calculations or any of the programming related stuff in any of these lectures, by the way. And keep that in mind for your preparation for the final. But I will also tell you next week what is on the final. The final will be multiple choice, by the way. How many questions I don't know yet, because I haven't written it yet. But it will definitely be concept-based and not implementation-focused.
Will there
Yeah.
be code?
No. That's what I meant by no. No source code. No source code, no calculations, no computation at all whatsoever in OpenGL or VRML. There'll be some general questions about VRML, general questions about the computer graphic concepts that have been covered so far throughout the course. And everything is based on the lecture notes as well. So, but I will give you a breakdown question concept thing next week. So. Radiosity. This is the other topic that kind of works in with ray tracing for the most part. Ray tracing is best used mainly highly speculative surfaces, things that cast shadows, shiny surfaces. So not characteristics of real scenes, really. How many shiny things do we see normally, and a lot of other scenes we don't. And we don't have that many specular surfaces. So rendering equations describe general shading problems. Radiosity solves rendering equations for perfectly diffuse surfaces. So here's some terminology for you. Radiosity refers to the lighting. So the energy of the light is the incident or transmitted. Must be conserved, hopefully. energy flux, which is the illumination flux, which equals the power and the energy unit per time, measured in lumens. So lumens. And then it depends on the wavelength, so we can integrate over spectrums using the luminous efficiency curve or something of that nature. We don't have to be responsible, again, for any of the calculations, but the terminology is what you're looking at, illumination. So intensity, brightness in particular. So how do you know how bright to make something? Well, if you cast a light on a surface, you're going to look at the radiosity of the diffuse surface that's not doing, it's not shiny, it's absorbing the light. Well, how much light is it going to absorb? Well, there's calculations for it to figure out the radiosity component of not only the surface, but the other areas around it, the air, the light that's in the room, as an example. So let's see, rendering the equation. You're considering a point on a surface. We always have a center point, or we have a spot in which we're projecting the light source. And then we can have a rendering equation. So it's the outgoing light is from two sources, the emission and the reflection of the incoming light. So you integrate it over all of the incoming lights and integration over the sphere, which is kind of an interesting concept, because if you think about the incoming light that's coming into the surface, or the, whatever, this happens to be a flat object, it may not be hitting all surface, and may not be hitting all surfaces. I may not be hitting a surface normal, it may not be hitting anything in particular, and it's not one point, it's not one pixel, it's a series of pixels, and it's not hitting it all at the same intensity. If it did, it'd look like a round white circle on a red object or something, where we don't see that, we see a little shading from a high intensity point to darker points that actually were from around the radius of that particular entry point. So that's what's referred to as the radiosity in terms of the illumination. So we take the incoming light source. We must account for the foreshortening of the incoming light, which is kind of an interesting concept as well. Really sophisticated graphic programs take into consideration the distance of the light source. If you're shining a light really close to something, then what we're looking at then is a higher radiosity. We're looking at something that's going to be brighter. Then if the light was farther away, you could experiment yourself with a flashlight, actually, and see the same effect. Don't worry about the rendering equation, but all of those factors I talked about, emission, direction, distance from the light source, all of those things play a factor in calculating out the radiosity component. And note that the angle is really two angles in a 3D, and a wavelength is fixed, actually. So we don't really worry about the wavelength or the angle, actually. So rendering equation is an energy balance. Energy is equal to, or energy in is equal to the energy out in terms of its equation, and you integrate over a hemisphere. So we have different approaches to it. You don't have to know about the different approaches or the rendering process. But radiosity, so considering the objects to be broken up into flat patches or flat surfaces, which correspond to polygons in the model, assume that the patches are perfectly diffuse reflectors, and radiosity is going to be equal to the flux, which is going to be equal to the energy per unit by the area per unit for the time leaving the patch. So what we're looking at is being able to put a number on that. In most of your graphic packages, you're putting a medium, light, medium, dark radiosity, or you're using a number scale to specify radiosity on the object, and the program itself is going to calculate this for you and give you the essential outcome of any particular function or method that would be performed. And the notation here is just going to get into the method implementation that we're not really going to be worried about, because we don't need to do the radiosity equation. In fact, you wouldn't do this either unless you were writing your own API. So I'm going to kind of skip through this part here. Here's a rendered image using the concept, so we can see the ray tracing and the radiosity. Actually, we see radiosity in terms of the illumination of the light on the surface, and then we can see the shadows and we can trace the light. So both concepts work together, by the way, to produce the realism of the image. If we didn't have any of the shadowing, and this is actually what I talked about last time in terms of ray tracing, is producing this. this kind of an effect that we actually see in this room as well, in terms of the shadows that are casted on the walls. This makes this look a lot more real, and given the light source, than if we didn't actually consider that. So here are the patches. So if we were to try to figure out how we're going to do this in terms of the radiosity, well, we can take this scene, work backwards with it, and say, how did we get here? Well, we took the patches that were in there. We applied a formula recursively to the patches. You can see the light sources up here on the top. And you can see the light source up here as well on the top. So the light source is basically going to be that in the in direction. That's going to come in to each one of the surfaces. So it doesn't even hit this one. It actually hits the sides a little bit, but it doesn't hit it as much as it hits this one, which is really facing it, or this one here, which is sort of facing it. So then we have all the other objects in there, and we take and we compute the form factor. So considering two flat patches, and this is the ceiling panel, and this is one of the surface normals, we can calculate where's it going to hit, and how, what brightness. Because if you notice, it's not hitting everything with the same level of brightness. That would look very fake, actually. But the surfaces that are facing out, or in fact, this sort of looks kind of fake over here. This should be probably darker over here, as dark as this would be over here. Because this surface really isn't being hit, but maybe it's being reflected. So we can calculate using the flat patches, and then use a differential patch to kind of figure out the foreshortening, you know, because the light's not going to be as strong at all locations. In fact, some of these objects are farther away. This one here is farther away than this one, which is farther away than this one, actually. Different angled, however. And then we can use the form factor integral to kind of calculate out the radiosity that should be applied towards the object. So very few cases where the integral has a simple closed form solution to it. It's a very challenging problem as well. Alternatives used for different methods. So there's a two-step process actually that you can go through to solve the problem. Here's an example of it being done, and you're not going to be required. Actually, even if you took an advanced computer graphics class, you're probably not going to do any ray tracing, unless it's maybe a third level or applied with a programming interface for OpenGL. Probably create one that works with OpenGL. But you're not going to do it for an application programming interface. But long story short, this is some examples of calculating the form factor 2 example. So you can kind of sort of see how you have to take the shape into consideration and the angles for which the light's going to be projected on it, and all of the information that would go into it, and then you're going to recursively do it for each one of the rays that's going to be casted. So it's not just a single, it's actually done multiple times to generate the proper surface illumination. So we're not going to go into the formulas for that either, but I just wanted to introduce the concept of radiosity to you as well, so you can sort of get a better understanding of that. We also have this concept of parallel rendering. So ray tracing works great when it's in a single rendering, one rendering cycle, which means the entire image comes out, goes in one end and comes out the other of the pipeline, and everything gets done sequentially. And so in many situations, a standard rendering pipeline might not be efficient. If you have multiple components, and especially if you have multiple graphic processors, or you have multiple buffers, might be better and more efficient to do it in parallel. So you need higher resolution displays, for example, more primitives than one pipeline can handle at one particular point. So the way you speed up the pipeline is to do it in parallel, have multiple pipelines, which is actually kind of popular these days. You know, if you think about the concept of the old days, even with our computer monitors, actually, if you think about it, we didn't actually have to have a graphic processor on there. We could run with the main memory on a regular old processor because we didn't have that much graphic. In fact, especially with a command prompt or something, there wasn't any GUI to it at all. And then when Windows came out, all of a sudden it was like, oh, graphics. And then games came out, especially even DOS games. A lot of rendering. But even small little, 512 memory or 256K memory on a graphics card works out just fine. Now we have like 2 gigs or 1 gig on a graphics card. And we have a separate dedicated GPU for it with a separate processor completely just to do the rendering. You're wondering, why do we need this? Because we have Windows, or we have the Mac, or we have a, GUI operating systems now where it's all graphics. Well, they'll take that and put it on a high definition screen, or take that and put it on a Retina screen. You're going to need a faster processor in order to produce images that are going to look good on that, and they're actually going to show up faster, and not going to flicker, not going to be degraded by the hardware. Excuse me, by the speed of the process. So to make more efficient use of the hardware and that capabilities, we have to mess around with the pipeline. Well, one pipeline has limitations. It's like a funnel, putting one in one end and out the other. So parallel pipelining is essentially the way of getting around that problem. Using parallel 2, how about 3, how about 4, how about 5? In fact, you can do the 4th scene in one, back scenes, the next scene. You can use an assembly line approach to actually process the scenes through the pipeline, which makes a lot of sense as well. So, when you want to use commonality components to build a system that can render in parallel, use standard networking to connect it, which is what you can do in essence. So you have this thing called a power wall. So where do we display large data sets? Well, CTRs have low resolution, 1 megapixel. LCDs, panels involve improving, but still expensive. Actually, they're a little cheaper. It's making of the slide set. And new resolution comparable to data sets to see the details in terms of, we can see more details, ocean data, all sorts of stuff. So use multiple projectors, multiple projector systems. So commonality, high end, and using systems. So we have this pipeline. So we take the screen, or the scene that we're projecting, and we break it out into 4 different components, actually. You can see this on hardware when it fails. When one of the pipelines is hosed and a square is missing. Then you know, oh, and then this is how you can take small little LCDs and put them together to make big ones, and each one of them is a portion of the graphic scene. So you take the entire projected image, break it out into 4 components, process them in parallel independently, and then project them out on the screen, which makes for a really nice scene generation. And that's the way you can make a huge monitor. In fact, those big ones you see, billboard monitors, can be done this way. If they're projecting a live video feed or something, it's better to render it in multiple parts like this. So these are called power walls, and they're tiled displays. And here's an example of one right now, actually. It's the ocean here. We have a lot of blue in the ocean, but we also have pieces of it. And this is in our panel display. In fact, you can do this on a Windows machine, actually. You can have a paneled, you've ever seen those things? You usually see them in movies, but now they have them in fries. It's like 5 or 6 different panels and all connected together. But they're all separate units, and it runs through one graphic card. The one graphic card puts it out into 4 or 5 different pipelines, puts it out into 4 or 5 different displays, and renders it in parallel simultaneously. So you can move the mouse, from the left hand to the right hand side. It gets rendered correctly. And the whole screen is panoramic in that point because you can kind of look around. It's called parallel processing, and it's parallel graphic pipelines is what it is. That's using either one main controller, with separate pipelines that are associated with it. They're all running in parallel. And usually one does hose, or one, if you've noticed it, if you've played around with those systems, one will run a little bit slower than the rest of them sometimes too. Depends on the memory, depends on how big the buffers are, and how well efficiently it is. So this is the tiled display. Actually, you can see that a lot in some big stores. You can put it on the entire wall, kind of thing. So in terms of our power wall for our graphics system, we can have a 6 dual processor, IntelliStations, a GeForce 3 graphics card, 6 commonality projectors of 1024 by 768 perhaps, a gigabyte Ethernet, because it's going to be run through. We have a connection that goes in between each one of these panels because the pipelines have to communicate with each other. It's usually done through the networking system, so that's why you want to use like an Ethernet cable. And you want to use a fast Ethernet connection because if one screen redisplays, you want the other one to redisplay too. As an example, if one mouse that appears on one screen is going to the next one, then you want that to actually update the one that the mouse left as well. So you need to communicate back and forth with it. So we also have back projected screens, perhaps it might be used for it, and then shared facility for scalable system groups or integrated operating system and network issues that might be worked with that as well. There's an example here where we got all of these different projectors that might be projecting something out, or maybe different screens that might be looking at different parts. So you can actually do this with Windows, believe it or not. Actually, I think it started with Windows 7. You can do it on a MacBook too. You can have a monitor to show part of the screen, and it's not mirroring. It's turning the mirroring off. And actually, I can do it right here with this one. But you're not going to see what I'm seeing. So I have this mirrored. But if you turn the mirroring off, my graphic card can actually handle. This is the upper left-hand side. This is the upper right-hand side. This is the lower parts. And just break it out into all the different screens. Hook up all the different screens to it. And there's your huge computer image that's all broken out. Each one of the screens is going through a separate graphic card. Each one of those graphic cards is doing the translation through a separate pipeline. So, software in your operating system has to support it. You can't just do that with any operating system, however. There's another example here with 3 different images coming through, and you can see this here. You may not be able to see it. There's 1, 2, 3, 4, 5, 6 different squares. You can't see the square. Actually, you can sort of see it. I'm putting it over a little line right here. But this image is being created with 4 different projector screens. Actually, it's projecting that image out here, and the image is actually going in parallel in terms of its processing. So in terms of the power wall concept, inexpensive solution, but there are some problems with it. Color matching. That's the interesting part. In fact, I've seen this at Fry's actually, because I've seen them do this. They take a bunch of monitors and they put them together on a wall, but they're all from different manufacturers, and they connect them to the same graphic card, and they do this power wall kind of concept with it. And then one of them's a little lighter than the other, or the colors change because the monitors have different qualities to them, so they're not being shown correctly. So this little square over here is a little darker than the rest of them, or something like that. Very, very, very hard. So what actually people do when they're going to do this seriously is they buy 4 of the same LCD brand, get the same hardware for each one of the squares, with the same graphic cards, with the same settings, and then you're guaranteed. But that's a lot of money actually to make it all match, which is what people do in networking anyway. If you want to set up a reliable network. Actually, if you want to have fast internet speed, use the same brand Ethernet card as the router, or as the access point or something. Go with something that's more standard, because then the settings are going to be more standard, and you're going to get faster cooperation speed. So color matching is a problem. Vignetting, alignment, overlapping areas, borders around each one of them. We don't want any borders around it, but how far is it going to go to the end of the screen? How much of a gap is there? Syncing, dark fields, or dark areas in between. So, in terms of graphic architectures, we have the pipeline architecture that we can consider from a CGI geometric engine, which is why those CGI actual machines are really good for this, because they have dedicated processors that can do parallel processing for you. So you can use these workhorse kind of graphic processing computers to do simultaneous rendering, for not only for video conversion, but for projection or for translation. So you can take and convert one video type into another, merge clips together, and take advantage of multiple pipelines and multiple processing power. So geometric passes through the pipeline, so we can have geometry passes through it, so we can take a look at the hardware for clipping and transformation and texture mapping, transform, click, project, store, resize, go to the screen. Eventually we have to, at one point, take and render this entire thing, but we can take all of the different single level pipelines and merge them together in a main pipeline. It's going to basically do the geometry for us, essentially. In terms of our building blocks, the graphic processors are hopefully going to consist of graphic blocks and rasterizers, geometric units for transformation, clipping, and lighting, and rastering, and parallelized, so scan conversions and shadings perhaps. Where to do the depth check? Well, that's an interesting point. These are all very multi-purpose, not generic. They're very multi-functioning, special purpose processing systems that are specifically designed for certain tasks. So sorting paradigm, so we can categorize different ways of interconnecting blocks using the sorting technique. So each projector is responsible for one area of the screen, so we can sort primitives and assign them to proper projector locations. And we have different algorithms that can be categorized for where the sorting might occur. So the sorting might be what's going to be put on what, because we have to eventually, because I have been talking about already broken out image. So we have 4 screens that are showing one image, essentially, or 4, but somebody had to break that out. So the sorting is going to break it out and figure out that this is going to fit over here, this is going to fit over there. Interesting thing is, all the 4 screens in the previous examples I've been giving you are assumed to be the same size. If we have different size screens, we have 2 big ones on the top and 3 smaller ones on the bottom or something. We have 5 or something. The sorting algorithm would have to be designed to work with that configuration, so it could give more real estate to the ones that are bigger, and smaller areas that are going to be given to the smaller display sections. So 3 rendering models can kind of be put together in terms of the concept. So first, sort first rendering, sort middle rendering, or sort last rendering. Sorting last rendering has its pros and cons over sorting in the middle. What it basically means is taking this big picture that we want to see, how are you going to break it out, and when are you going to break it out? Not only how, but when. So most efficiently, you could probably break it out in the beginning. If you did that, then you can have parallel pipelines with different memory allocated to it. So your bigger, more labor-intensive ones from your sorting routine could be fed through more memory utilizing pipeline, perhaps, so that the graphics actually come out and rendered quicker or faster at the same speed, given that they're not all the same size. If you do it in the middle, you could sort it from from a post-tense kind of concept in terms of what you're going to put together. And you do it at the end, may not necessarily render, but might be actually faster if you're just going to send everything through, process it as fast as possible, and then sort it out at the end to see what's going to go where. Which means you can have generic processors, generic pipelines, here. These are not generic, these are custom made. So they're gonna change depending upon, they're gonna be more flexible. So if you sort first, each rastering unit is assigned to an area of the screen. So we've already pre-assigned it. Each geometric unit is coupled to its own rasterizer. So most sort primitives first can use commonality cards. They can all be the same because you're going to sort it out equally, hopefully. So here's a sort first rendering for a random triangle application. So doesn't really have any kind of scene. It's just random triangle generation. So if you sort in the middle, then the geometric units and rastering units are decoupled. So you have to do it twice. So each geometric unit can be assigned any group of objects. So you can have more generic processing going on, and each rasterizing is assigned to an area of the screen. So you must sort between the stages. So you have multiple processing and multiple sorting going on versus just one stage sorting. And if you sort it last, is coupled rasters and geometric units. So you can assign objects and geometry units to load balance for better application control, which is what I was saying before. This one, it doesn't really matter what these are. These can be generic, and you can just load balance, meaning divide the work out evenly among all of the parallel processing that you've got going on, and then at the end put it together and sort it out and figure out which display you're going to send what to, given that you have adequate bandwidth to get it to at the same speed for each one of the displays. So we can also do what's called a tree composition. Compositing. So compositing in pairs and then send the colors and the depths to the buffers, and then each time we do a half processor become idle, we can essentially go back through the tree and traverse another branch of it. So we have the application with all of the different components that are going to be displayed, and then take and break it out for the different pipelines that you might have put on there. A binary swap, compositing, which each processor is going to be responsible for one part of the display. So you're basically taking the display, instead of taking the image that's going to be sorted to put out on multiple displays, you're taking the display and going backwards, breaking it out into smaller components and saying that this pipeline is going to be responsible for this quadrant, this area of the screen or the display, and that one's going to be responsible for that. This is what happens with the settings on most personal computers versus the, when you do the mirroring versus the spanning. So it's turn the mirroring off. Then you're going to have essentially that screen is going to be responsible with a different pipeline than this screen would be. Then you're going to render it in parallel, but you're going to do it with two separate screen definitions or display definitions. And then you're going to basically look at the adapter to control the two of them together. So in mirroring, you might actually just look at one. So here's the last sort lasting rendering for a random triangle application. So not really going to show us very much, rather than it's just a random. We see more randomness actually happening in consistency. If we compare this first here, we see that we don't have as much consistency between the screens in here because we're sorting it first and then we're taking the random generation and we're displaying it instead of taking the random generation and displaying it out last. So we're sorting it last, which means we have more consistency in the number of triangles that were randomly generated for each one of the quadrants, so or the squares on the display. It gives us different visual effects, let's just say that. So we figure out which visual effect we want for the best output, and then we can design the parallel processing for it. So the formal comparison, the sort first is appealing but hard to implement. The sort the middle is used in hardware pipelines. So most difficult to implement with add-on commonality cards. You have to have specialized hardware for it. And the last is the sort last. Is easy to implement with compositing stags and creates more network traffic because you've got to take everything after it's already been rendered and combine them all together and then sort them out to each one of the locations. So your networking traffic is definitely increased. So we can do mapping to clusters if we wanted to. So for different architectures, shared versus distributed memory, communication overhead, parallel versus distributed algorithms, the different scenarios lend themselves to better solutions. Easy to do the sort last in this because we have more functionality for the networking components. So we can configure that differently. Must evaluate the communication cost to make sure that increase in network traffic, computational cost from the network perspective, is going to be worth the expense of actually performing that technique. Must evaluate everything. And standard evaluation strategies are incorrect if transparency is used because it's not going to essentially do anything for us. So not going to go through the rest of this because we don't really need to know it. What I wanted to do is give you a brief introduction to the concept of parallel processing and some of the things that are involved in terms of configuring pipelines for it. So the rest of this is going to be overkill for the introductory course. But parallel rendering has to do with when you're going to sort the data. You're going to do it before, the middle, or the later part of it. And what visual components do you have to really consider in terms of that. Okay, so now we have two concepts to look at, or actually two continuing concepts, event-driven programming. And the concept of animation, this one is called Event 1 and Event 2, and they're at the end of the lecture set, which is really kind of the last sort of set of lectures that I normally cover for this course. And this is based on OpenGL because you don't have these capabilities, well, you do have capabilities, but they're not quite as easily defined in terms of the programming component of it in VRML. So in VRML, it's all automated for you. In OpenGL, you can program it yourself and create the special effects. So event-driven has to do with a mouse click, a keyboard, something happens from the user. Animation is the exact opposite, but it's all the same thing. You're going to move something from this coordinate system to that coordinate system, or from this location to that location. You're going to raise something, you're going to lower something, you're going to do something. So you can do it with or without user input. That's what I'm saying. If you do it without user input, you're creating animation. If you're doing it with, you're creating event-driven programming. All the concepts essentially are the same. If you're doing animation, you're dealing with timers. We're setting a timer. In the programming, you set a timer in OpenGL actually. And at certain intervals in the timer, actually you can do one in VRML as well. At certain intervals, you're going to do something. And you're just going to rotate or translate, essentially. If you're not doing animation with a timer, you're doing event-driven, then you're looking at mouse clicks or keyboard keys. So you can use the keyboard keys, the up and the down arrows, or actually any key on the keyboard can be used for this. Or you can use the mouse, essentially, to capture events that are going to be used, and, well, to generate the events, and you're going to capture them in the program. So by definition, event-driven programming in OpenGL is the programming responding to events. Events are handled by the user and defined by the callback function. So we have callback functions that do this, and the callbacks must know the context of the event type passed through the variables, knowing where was this, what did you click on. Not that it was a click event, but where did it go? So when you're designing graphic programs, and the reason why I'm showing this to you in OpenGL is because this is more of a programming language interface. So OpenGL is the API that's used in C or C++, or Java. So from a programming perspective, if you're going to write a more elaborate application of this, you're going to have a main event loop that's going to run as a state machine, essentially, of your program. And inside of your main event loop, you're going to have the different handlers defined, one for the graphic display, one for the keyboard, one for the mouse. You may also have a different graphic handler, or excuse me, a handler created for, let's say, a joystick or another device, a pen or something. So those will be all your input devices, and your output devices are going to have handlers. And the handlers are going to be created so that they respond to the main events that occur, that are captured from the main event loop. So here's a simple example. It is done in C. Don't worry about it if you don't understand C programming. This displays a square on the screen. And what this is going to basically tell you is that we're running a loop. We're going to do a recursive kind of, well, OpenGL itself runs recursively in a loop. We always have this thing called the state machine, which is the main program. So we run init that initializes it, and then we run the main loop, and the main loop is going to go loop through and check for events as well as display things to the screen. And in this particular case, we're just creating a rectangle square, and we're putting a title on the window called Simple Galette App. And we're not really doing very much, but we're going to create a window handler. And then we have this display callback, and then the callback is called when the window is redrawn or drawn initially. And we're going to redraw the window, which means if the user clicked on something, move it, or do something with it, which means we're going to respond to the event. The scene's going to change, so we have to redraw the scene. So essentially the redraw is going to clear the graphic buffer, populate it with all the new information that now exists, and then swap those buffers, put it back out there on the screen. So more on the additional Galette features can be used to position the window, position a shape. We can actually move the window across the screen, move shapes in the window. Additional callback functions also exist for the mouse, reshape, motion, a keyboard, special functions that can be handled as well. And then we have the reshape callback that can be used in part of the graphic system. So it's called when the window is resized. Again, so the reshape will take it, and you know, the reshape, think of this more like what you've normally seen in older web browsers actually do this. Newer ones don't really do this anymore. So to reshape something, let's say you had a window and it was really big and you made it smaller. Well, if you really reshaped it from a graphic perspective, you drag the window and made it smaller, everything in there should become smaller. That's reshaping. Resizing, refreshing is to paint it out again. So if you're going to make a window bigger or smaller, you're not just going to put a scroll bar on the left and the right, you know, which is what Windows does, you know, to go to the left, to go to the right, because now the surface area is smaller, but the image inside of it's still the same, which is no reshaping. So the reshape, you're resizing it. It's like what you do with pictures, actually. This works with pictures all the time. And it's a graphic processing kind of like a, you know, when you take a picture in a preview window and you open it up, you make it bigger. Well, the picture becomes bigger. Make it smaller, the picture becomes smaller. That's reshaping, resizing as a concept. We also have, and this happens when automatically on the events in which the window itself is resized, or objects inside of the window are resized or reshaped, or dragged or moved. we have those callback events that occur. And callback events is kind of like handler intercepts. So the callback, by definition, is the communication between the receiver of the signal, I'm going to call it an interrupt or a signal, which is actually interrupt based, and the callback is what hands it over to the handler, essentially. And so we create functions for this to deal with different events that are going to occur. So called when the mouse button is pressed as an example. We have the mouse button. Well, we can actually capture, so what mouse button was pressed? The left mouse, the right mouse, the scroll? Was it, you know, what mouse, essentially, a controller are we intercepting? And then we can take the position, the XY position of it, and go, well, they clicked here, they clicked there, and use that actually as part of our graphic system. And we know that VRML actually has this built in automatically, because you just click anywhere and automatically the callback is created and it does something for you. In fact, you can create VRML images that load up websites and stuff too, as we've seen. So called when the mouse is moved around with the button down, as an example, held down, all of the events associated with the mouse. So we also have keyboard callbacks, so called when the button is pressed on the keyboard. So, well, if you take this from a computer perspective or from operating systems perspective, every time you press something on the keyboard, every time you press something on a mouse or any type of input device, you get an interrupt. The interrupt is caught by the operating system. The operating system takes it and converts it into a handler, and the handler delivers it to the user through the user mode from the kernel control. Same thing happens with the graphic system. So a keyboard is pressed, graphic processor, or the graphic system itself that's running the program is going to hopefully catch from the kernel or from the operating system the interrupt that is being generated and be able to process it through its own handler. So these callbacks are essentially responding to the events to perform the message that's going to be sent to the handler that's going to take care of the processing of whatever's supposed to occur. So it's kind of a very primitive approach to actually doing this, which is why this works in C or C++. In Java, it doesn't really work in higher level APIs, because higher level APIs are abstractions on top of functionality that's going to be automated for you, for the most part. You can still have control over the keyboard and the mouse, you're just not going to be able to capture those events and handle them specially, unless you're going to use a lower level, like a C, which is not really that low level. It's not assembly language. So in the old days we used to call low level assembly language. Now we call low level C, which is, you know, third and a half, almost fourth generation actually, if you think about it. So don't know anything about programming language generations. That made absolutely no sense to you. But in any case, I was just trying to make a point. So animation callbacks, called when the system is idle and the system wants to do something. So we have animation callbacks. I'd say, let's say for example, we have a float time, and the time's going to be something. So after something elapse, rotate something, or post redisplay. We call this method to move something, and then after it's moved, redisplay the screen or something, or which is how we create animation in terms of that. So it's all done through the same way. Menu callbacks. We can put menus. Actually, you can create menus in your VRML as well. Menu displays, you know, we're going to put open, close, run, different menu options that are going to exist. And what you can do on there is just create functions for each one of the menu options. And when the menu option is created, the callback is going to be initialized, and the callback is going to send and, you know, call whatever function was specified for that particular event. So that's the first part. We also have the second part coming up. And don't worry, this is the last part of the dry stuff for today. Only 33 slides, we'll get through it in good time here. So let's take a look at it from a function point of view. So this is part of the GLET library, and people wondering, well, you've been talking about OpenGL, but GLET is part of OpenGL. So if you go to download OpenGL APIs, it usually says GLET on it, because OpenGL is the graphic rendering, and it's the shape definitions, and it's all of the graphic components. GLET's all the user interface components, and all of the callback stuff as part of GLET. So it's the event-driven library, or the API, that works with OpenGL. It also works with other packages, but it's mostly primarily used with OpenGL and WebGL, something like that. So programs that use Windows, input and output. They wait until an event happens, and then they execute some predefined code, as we've seen before, according to the user's input. And then the events, as we've talked about before, which are the key presses, the button presses, the press and release, the window resizing and stuff. So here are the function calls that actually come into place here. And these are built-in, predefined functions that respond to events. And this is all part of the GLET library or API. So it's the routine to call when the event actually happens. When you have a window resize and redraw, as I mentioned before, we also have a user input or a mouse or keyboard or any other input device that's recognized by the computer. And then we have our animation, which might render many different frames actually, depending upon what type of animation we're doing. So we have the thing called the register, and register callbacks and sends the information with the GLET methods or functions, depending upon what environment you're working with. So the display, the function, the keyboard, the mouse, which is going to send essentially whatever information is necessary for that processing. So we have this thing called an event queue, because if you haven't figured it out already, what ends up happening is the user presses a bunch of keyboards, or moves the mouse all over the place, or clicks too fast, and it doesn't happen in real time. So instead what ends up happening is the same thing as an operating system. We have any queue or a table or something that's stored that keeps track of all these interrupts that are being raised. And so we take this and we calculate out, well, which one came in first, which one came in second. And then we can process them sequentially, because these things might be happening in parallel. As a classic example is when people press keys and mouse click simultaneously. You're going to get simultaneously parallel processing, which is not such a good idea if you're doing it sequentially. So we put things into a queue so we can run through them and process them. So we have the mouse, the keyboard, the window. They might all end up in the same queue, or they might be put in separate queues. And we might actually have a preference so that the mouse goes first, the keyboard goes second, the window goes third, or maybe we do them in parallel. Depends on our processing technique. So we have a main loop, and the main loop is going to go through the mouse call, the keyboard press, the window call, all the different components that are going to come into this. And then the queue is going to essentially, allow us to keep track and not lose anything. So the rendering callback here, the callback functions, where we're going to draw, where all the drawing is going to be done. So the display function is one of the default OpenGL functions or methods, as called. And here we have, we're going to clear it, we're going to begin it, we're going to create a triangle, here's the vertices of the triangle that we're going to use. Here's the 3 points that we're going to make up this triangle, and then we're going to end it. So we have a GL end that says, we're done drawing, move on to the next one, kind of thing. So this is the rendering callback, which does the displaying, and then we have the idle callback, used for animation and continuous updates, as mentioned before. So when it's idle and, well, nothing is happening, after we've painted the system in our graphic loop, we have this idle time, where things just stay on the screen. During the idle time, then we can rotate something, move something, transform something, and we do that, and then we do a post redisplay. So after it's been displayed, we're going to move something, and then we're going to redisplay it, essentially. Which, if you think about it, that's kind of like what our operating systems do. It puts stuff out, and then we click on something, and it opens it up, displays it, we minimize it, it minimizes it, it constantly redraws. So our operating system interfaces for driven programming is pretty much mirroring what we're doing from a graphic perspective in terms of creating graphic applications that are doing this. We have our user input callbacks, and they're all specified as callbacks, by the way. So processor processes the user input regardless of what source it comes from. So if it's a key, you're going to pick up, well, what key was it? So if you remember, like a lot of the OpenGL games, in fact, there's a ton of them still out there that worked in a DOS environment. They use keys, like arrow keys up and down, or sometimes you use like the S and the L, and you kind of back and forth to shoot something, or to, the keys meant something. So you basically captured the key input, you send it to a handler to say, hey, the L key was pressed or something, or the Q key was pressed. Q was maybe for quit or something. So then the program would quit or something, or ask you, hey, did you want to save your score? And end. Believe it or not, all your graphic programs that are running on game consoles, Game Boys, and so it's doing the same thing. There's an event, a callback that looks at the console, whatever happens to be the device that's being used, what key was pressed, what button was pressed, and then correlate it to a handler, and the handler is going to change your graphic or it's going to do something for you. So you can have a machine gun that shoots you know, or a knife that moves or a hand that moves, and you have all the, it's primitive, but that's still what we're doing today, however. So I shouldn't say primitive, it's very basic actually, not too hard. Actually, game programming with OpenGL is pretty easy compared to some of the other things that are out there that you could possibly be doing. Mouse callbacks, use the mouse obviously, so the keyboard. In terms of the keyboard, a user input, or switching here, this is C code to take and switch the key that's being captured, and what is the key? In the case that it's one of A, B, C, D, E, F, G, whatever. And on the mouse, we want to know the button maybe, we want to know the point that was pressed, captures the mouse press and the release events. The mouse functionality itself is going to be very similar. If it was the left button and the state was that the left button is down and it's still down, or if it's a double click or it's a single click, or maybe it was the wheel that moved or something, we can capture that. So here's a kind of a summary of all of the events in OpenGL that can be captured. These are just for the basic keyboard and mouse. Obviously you can put on extension libraries for other you know, console devices that you can possibly connect to the computer through game ports or through serial ports to control the game or to control the animation. Key presses, mouses, motion, windows, system, and software. You know, what to draw, timers, idle timers, and stuff like that, which are going to give us our animation. And we know that we also have the OpenGL primitives, geometric primitives as well. So the geometric is specified in the form of vertices, so there are 10 primitive types, which actually, believe it or not, correlate to different types in VRML. So VRML, we work with shapes. In OpenGL, it's more of the primitive and geometric primitives. So we have lines and dots and strips and triangle strips and fan strips and stuff and polygons that we're working with. And we put these shapes together. If you think about what we looked at before, and this is sort of an introduction to OpenGL as well, just to kind of, you know, give you sort of the impression that it's not so complicated as you might want to think it is. But in terms of looking at the primitive shapes, we compare these with being able to create them using functions, and the OpenGL command format sort of looks like this, where the function itself is broken out into different components, and it's the name of the function. So it's very primitive. It's not like, if this were rewritten, I think today, using object orientation and polymorphism, probably be a more effective library. In fact, there are revisions of it that basically have done that. But in the old days, we didn't have methods. We didn't have overloading and overriding. We didn't have anything. So we just had a bunch of functions. And so if we take and create a bunch of functions, how are you going to make one work with integers and one work with floats or doubles? How are you going to make one take on 3 points and one take on 4? Well, you just create a new function for it. And then you call the function that you need. So in this particular case, we have different data types. So this, well, let me start with the left here. 3 is the number of components. Is it an XY or is it an XYZ? Or is it going to be XYZW? Here we're going to do 3 dimensions. We actually have 2 dimensions, just X and Y. We put into it. So how many are we going to give in there in terms of the components? Well, that's a, you know, second one is the data type. F is, you know, standard for floats. D is going to give us a double, I for an integer. And then we have the V on the end here to say that, you know, the vector. So omit the V for scalar. So we can do here 2F, so we don't have the third for the vector kind of information that we need for this. So, which is kind of interesting, actually. All the functions are written like this. So this is for, you know, primitive, kind of to one point we have a GL vertex 2, 3, 4, followed by F, all these combinations. And we have different function names for each one of them. So it's kind of easy to remember what you want to use if you think about it in terms of what it is you're trying to create. So vertices and primitives, they're specified using the GL begin and the GL end, along with the primitive information that you're going to pass to it. So you begin to do something, you draw it, and then you end, which means the shape's done. So in VRML, you just say shape, create a new shape. In OpenGL, you have to actually go begin, specify everything out, end. So there's a lot more lines of code to it. There's a lot more creativity to it. However, you can design your own primitive, which you can't do in VRML. You have to use built-in ones. So a lot more flexibility, a lot more creativity can be done in OpenGL. So the primitive type determines how the vertices are going to be combined. So in terms of the shape that we're going to essentially combine to create. And so we can also have, like, for example, red, green, and blue in terms of colors for GL float, or other coordinates might be, you know, arrays of coordinates. So here's an example down here of a GL primitive, and the primitive is going to be essentially going through a loop and taking the color schemes and applying them to the coordinates that we're going to specify. And here's an example here. This particular function draws this particular shape that's over here. So this is a little bit more work than the VRML stuff. So if you haven't done any of the assignments yet, know that I gave you the easiest way possible to create shapes. VRML is pretty easy in terms of creating the shapes. Because the last time I taught this course, we used OpenGL and we did it this way. So this is a little bit more complicated because you have to use a programming language for it. And you don't necessarily have the same capability to get the same vertices to draw it out this way, but you can do something very similar to it using predefined coordinates that you're going to program into VRML. And I've actually seen some of your assignments already, and some of the spaceships look really cool, actually. If you get past the spaceship, that's the beginning. As you get a little bit further into it, it gets a little bit more complicated. However, it's very doable. So don't give up on the VRML stuff, but I wouldn't wait till the night before to put it together, because you're going to end up with problems if you do that. So, and that you're not going to learn anything either. So, the more you play around with it, you actually might find that it kind of gives you a better understanding of how those shapes are created in terms of the vertices, and you know how you're going to apply the transformation, rotation, and stuff to it, which is actually kind of fun when you think about it. So, here's a drawing of parallelogram. So, you know, see where the red color comes into place as well. So, vertices and primitives, the points and the GL points, individual points that can be drawn. So, also another example. Lines, GL lines that can be drawn here. So, pairs of vectors interpreting as individual line segments. So, putting them together using, and this is the primitive type, the GL underscore line, the GL underscore points, different, you know. Then we have the strip, the line strip, which is essentially going to give us continuous lines. So, line strip is a series of connected line segments that continue in a particular direction for a particular depth. So, and then here we have the line loop. The line loop is going to create a circle out of it. It's going to close it. So GL line looping here. Not exactly a circle, but it's still looped. Still close. So line strips, so segments added between the last and the first vertice. So we're connecting the vertices together. Here's our polygon, which is kind of interesting. So boundaries of a simple convex polygon in this particular case. Triangles. Sort of like a triangle, 3 points instead of a line. So triples of vertices interpreted as triangles. And then our triangle strip, which is a bunch of triangles that are kind of repeated. So linked strips of triangles that repeat together. And these are all the built-in primitives, that you use these to create all the different shapes. So you use these to create squares, I don't know, spaceship components. So it's a little bit more primitive. Triangle fans, linked fans of triangles together in this particular case. Quads, quadriceps, interpreting as four-sided polygons put together in terms of, you can do strips as well. Here's our strip version of the same thing. Instead of using a triangle, you're using a rectangle quad. So linked togethers. So vertices may be 2-dimensional, 3-dimensional, or 4-dimensional. Can you see it really though? No, because we're really looking at 2-dimensional and a 3-dimensional display. So it's not necessarily going to be 4D, but that's the direction things are going in. 2D coordinates are promoted by 3D by assigning the Z value to the 0, which is what we've been doing actually so far. 4G homogeneous coordinates are reduced to 3D by dividing the X, Y, and the Z by the W coordinates, if not 0. Between the GL begin and the GL end, those are the commands that are allowed. This is just a subset of the commands that are allowed. Yes?
Is the fourth dimension the direction?
Has something to do with the direction, yes. But it's something that we can't see. So unless we rotate the image. So we're really looking at 3D right now. And humans see 3D. I'm not sure if other animals see fourth dimensions, but transposing, depth, direction. In fact, our 2D turns into 3D on our 2D displays. We have 3D, we're doing it on a 2D display by using a 0 for the third dimension. So it takes the 3 and flattens it to a 2, and then we can rotate to give us our 3. So it's a makeshift 3D. But we are doing 3D graphics though. 4D graphics, not quite there yet. So, unless we had non-flat surfaces, perhaps. If we had surfaces that were, going back to the parallel processing and the displays. If we create a box, for example, we'd have true fourth dimension. If we were sitting inside of a box, we had walls ahead, because we'd have the depth. And we'd have the sides and the front and the back facing, and we could sit in the middle of it. We could probably create a 4D experience out of that. But you can't do it by looking at a flat surface. So it's going to be two-dimensional. These are the allowed. This is some of the allowed components that end up inside of the beginning and the end. So setting the vertices, the color, I don't know, the index, the normals, so the textures, and multi-texture coordinates. Texture coordinates for multi-texturing can also be done. Controlling the drawing of the edges and stuff like that. So it's just more methods. There's a ton of methods, or should I call them functions? There's a ton of functions that get created that can be used inside of the opening and the ending tags. We have GLUI or GLET-I, which is the GLET-based C++ user interface library, which provides controls such as buttons, checkbox. And it's the UI GLET, essentially, because people like to put things together that look like web pages, with text fields and labels and buttons and stuff. And you can do this in OpenGL, actually. You can create a form if you wanted to, radial buttons. And there's a separate item for that for the user interface. So we're doing system independent. So it relies on the GLET to handle all of the system-dependent issues, such as windows and mouse movements. It's not like using the MFC library or using some sort of COCA interface, depending upon the platform that you're on, to create window motifs and stuff. You're doing your own, which is why a lot of the OpenGL programs look like foreign. You're like, what is that? Like the window doesn't look like a Microsoft window, and it doesn't look like a COCA window either. It looks like a OpenGL window, which is what you get actually with Java. If you've ever used Swing and used any of the AWT, Abstract Window Toolkit foundations, the window doesn't look like a Microsoft window. It doesn't look like a Mac window. Although the window doesn't look bad, it looks different. It's a Java window. You get that when you open up, in the old days, you got that when you opened up like NetBeans or something, which is a Java program, Java window, written in Swing. So. We also have, in terms of the GUI controls for the user interface, we can manipulate them through a kind of a GUI menu to set list boxes and stuff and control each one of the items through properties or control setting. So, simple programming interface as well that adds with this particular concept. So provides the default values for many of the different parameters in the API and several different ways to create and control them. As an example, we make an instance of the GLUI event, and we can add a checkbox, and it's going to be a click me, and we can add a state for the checkbox. It's selected, it's not selected. Add an action listener to the checkbox, so when it is selected, do something. Close it or do something else to it. So the usage for a standalone GLUI window, integrating the GLUI into a new and existing application is very straightforward. So steps are add the GLUI library to the link, such as the GLUI 32 library for a Windows system. Actually, if you get download something like Bloodshed or Dev C++, and you go through the library upgrades for the system, it'll have options where you can select OpenGL or GLUI, and essentially, automate the process in terms of the project type. So you go in and you select a project that is of type OpenGL or GLUT, and it automatically includes the files you need, such as an example, the header file for glui.h as an example. So you include those in, and then you make instances of those objects, or you call the functions, depending upon what type of environment you're working with. Works in C, works in C++, works in Objective-C, works in Java. So it depends on the programming language interface as to how you're actually going to create instances of objects or run functions that work on objects. And there's many different versions of this library as well. It's not exactly open source, but it's close. It's free to use, but it is owned by somebody. So register your callbacks using certain methods as well. So I'm not going to go through nobody in here is probably going to use this from a programming perspective, but if you wanted to, you can kind of see it's very straightforward. So some references if you want to. There's this thing called the Red Book out there. Actually, I'm going to click on the link and see if it works. See if it's still out there. Internet sites reports that item requested cannot be found. Okay, so the link is not going to be updated. So do a search. Oh, this one actually looks like it's working. Do a Google search on Red Book, OpenGL Red Book. Actually, I'll do that in a few minutes here. So this one here is the computer graphics. This is the second link. You type on here. Actually, I'll just do it here. OpenGL Red Book. There we go, PDF. If you want to get into this area, here it is here actually. It's not a bad source. It's one of the best. It's called the Red Book because in the old days, this looks like a reprint of it. There's probably available in PDF terms, PDF downloads for ebooks and stuff. It's probably one of the best OpenGL references. It's going to go through as an example color, lighting, blending, all the different functions that are available for each one of the different characteristics that you're going to apply, and then how to set up with sample projects, how to set up the graphic environment to capture the mouse events or the keyboard, or to do something specific. So, just kind of a brief overview and example. Essentially, some of the resources that are out there. There's a lot of resources out there on OpenGL. Actually, it's one of the most highly supported languages. There's actually a lot of resources for VRML as well. And one of the things I wanted to show you before I ended today's lecture, because next week I'm going to go over what's going to be on the final exam. And one of the things you might want to do is take a look at some of these PDF files that I've got loaded out here on the bhacker.com website. And let me show you where they're at, actually. I thought I saved the link. There we go. So one of the things you're going to need to do is kind of figure out how am I going to pass this final exam. What am I going to look at? Well, if you go into the computer graphics directory, you're going to see all the recorded lectures, but you're also going to see in here this lectures link. Click on the lectures link here. You're going to see, let's see, about 42 individual lectures. They're all of about maybe 10, 15, 20 slides each or so, not too bad. But down in the bottom here, you're going to see one called ID Spec, Pixar, Advanced OpenGL, Modeling, some of these other ones, and I've kind of downloaded them here so you can sort of see, as an example, the ID Spec. It's actually a article called The Wizardry of ID, which is looking at video software, video gaming, resolution, and it kind of gets into video graphics and game graphics and computer graphics used in gaming. So it's not a bad, it's an interesting article. It's about 6 pages long, but it kind of goes into, here scrolling with the action of the scene and kind of the creation of what goes into the planning process of the system, and then ray casting here for 3D rooms, and how the system is set up using the fundamental concepts that you've kind of seen in this class. So it's nice to actually kind of read through to see, wow, I recognize, I know what ray tracing might be and ray casting, hopefully, and I might be able to understand, and actually when you start reading through some of these articles, it's kind of interesting what you can pick up. The 3D survey, this is about 143 pages. It's a book. It's a textbook, actually, and this is the one that's called 3D Survey 1. And if I go back here and we take a look here, we have Survey 1 and we have Survey 2. And the Survey 1 is 143 pages. It's a PDF book. It's a free book, actually. It gets into coordinate-free geometric programming. It's a little bit advanced. Hierarchical modeling, hidden surface algorithms, context-free geometry, and stuff like that. It's not a bad, the different lighting, different shading models. If you're not happy with the PowerPoints and you don't understand some of the information when you go back through to do your review for the final, you're going to find this probably very helpful as well. So it's just another source of additional information, so you don't have to do a Google search, actually. That's the number one. The number two here is only 4 pages long. It's an overview of three-dimensional computer graphics. It's not too bad either. I picked this article out because it does a nice overview of what's involved, specifying the scene, the rendering, the storing of the display, what's involved with putting together the scene from a 3D perspective, and the CD, the different lighting models, the different directions, the camera angle, stuff like that, which is not a bad resource as well. And I believe I've given you all of the good resources from there. Pixar is actually kind of an interesting one too. I'm not going to open it up. It's going to go through like Pixar graphics, and it goes into some of the graphic systems, some of the animations and stuff that work with that. Anyway, so what I'm going to do next week for you is I'm going to write the final exam. Well, I'm going to write the final exam this week. And next week, our class is going to consist of a review for the final exam. So you're going to see everything that hopefully you're going to need to know. It's going to be multiple choice. I don't know how many questions yet because I haven't written it yet. All of the assignments are going to be due on 12/14. There'll be 2 different versions of the exam. So if you take the exam, because it's going to be offered on 2 separate days, same level of difficulty. However, what ends up happening is with ITU is like if students take the exam before somebody else takes it, it gets posted on the internet, stuff like that. So anyway, long story short, to avoid the cheating problems and issues, there's 2 separate versions of it. You can take it on the 12th or you can take it on the 19th. Actually, it will be offered for 2 separate weeks. If you've got the email message, you're probably aware of this already. It's going to be offered on the 12th or on the 19th, your choice. So you just get 2 separate exams. So don't come and have half your people show up on the 12th and then the other half show up on the 19th and expect to take the same exam. It's going to be different. Same format, multiple choice, but the questions are going to be different. So, but that kind of solves a lot of the problems. Most people will probably take it on the 12th, I would think. If you take it on the 12th, you do not have to show up on the 19th. The 19th is optional. The only day that's mandatory that's left is the 5th, which is next week. And then we have either the 12th or the 19th, depending upon when you're going to take it. So you must show up on one of those 2 days to take the exam, and you get credit for showing up on one of those 2 days. You don't have to show up on both days. So if you know you're going to be here on the 19th, don't show up on the 12th. You don't have to. You don't have to show up on the 12th to make attendance on the 12th either. It's the same for the 2 weeks. Questions? Comments? Concerns? No? Then that's the rest of the new information you're going to get for this course. So next week, I'll be reviewing old information and telling you what you need to study and hopefully pinpointing you to lectures that you should look at. After I write the exam, I'll know what the content is. So I'll be able to tell you what percentage is on this and what percentage is on that. If you're going to try and pre-study for it, right now I would actually do the assignments. I would actually get those assignments cracked out because those are going to be due on the 14th. They're going to be due on the 14th whether you take the exam on the 12th or the 19th. And they're going to be due on the 14th. There's no changing of that due date. And if they're not turned in by the 14th, I cannot take them in email. They must be uploaded. Another thing to keep in mind is if you think, and I had a student ask me this earlier before class, if you know that your VRML image only works in Cosmo Player and the animation doesn't work in something else, or it doesn't work in Cosmo Player or something, you can leave me a little note. It tells me that. And then I know what plugin to use, or what plugin you used, actually. It might help me figure out what plugin I should test it with. And I got all the plugins, so you don't have to worry about the plugins. It doesn't really matter. It doesn't have to work in all plugins, as long as it works in one. Hopefully it's the one you're using. Then you're in good shape. And I'm not really grading you on your ability to make it work with a plugin. It's your ability to actually implement the features that I asked for. So, and how closely you followed the description and whether or not you did it yourself or did you copy somebody else's. And as everyone knows, you have to do your own work. So, now do we have any other questions? Now then, the TA has started the attendance process. So we'll let her finish with that.